Okay, as we get started today, I would definitely suggest that you make sure that you have your um, ebbing text that I made the copies for you. At the beginning, it says Chapter 6, Thermochemistry. Please make sure that you have that handout available to you because we're going to be referring to pages out of that, and you'll definitely find it helpful to have that in front of you. Um, so we have two different topics here. Excuse me, I'm trying one more time. Thermochemical equations, and then applying stoichiometry to our delta H. Remember, that is enthalpy. So basically, to just kind of put it all together, you're going to see a little tweak on a regular old chemical equation, and then you're going to see how you can begin to use this delta H value to your advantage. Basically, I want you to think of it like this. So far, you have been learning little bits and pieces kind of along the way. And it's like you're building a toolbox. So this toolbox has to be equipped with as many tools as possible. And then as we continue to add things into our toolbox, we can do more and more complex problems because we now have more tools. If you think about building a house, you're going to need a lot more than a screwdriver if you want to build a house. And some of these problems, as we begin to get into the complexity of AP chemistry, they begin to be questions that sort of feel like we're building a house, and you have to use a lot of tools. So this is going to be one tool in a way that we can use our delta H values and equations, and it will all then just help you to get better at everything that you're doing here. So and by the way, none of those house building problems are in this presentation, so take a deep breath. It's all right. All right. So moving on. Applying stoichiometry to thermochemical equations. So the way that we apply stoichiometry, whenever we talk about applying stoichiometry, really what we're saying is that we're going to be able to use something as a conversion factor. When you think about metric conversions, when you think about stoichiometry and using molar ratios, these are all things that allow us to convert from one thing to another thing. And that's what delta H is going to be able to do also, which is pretty cool. So we're going to consider this reaction. We have a reaction here of methane and oxygen gas, carbon dioxide and water. So again, this is a combustion reaction. And there is a delta H determined here to be negative 890.3 kilojoules. Is that exothermic or endothermic? Okay, good. I think you said exothermic. So what we may wonder about an equation such as this, basically to put a problem to it, how much heat can be obtained from 10 grams of methane? Now, please understand, do we have 10 grams of methane? I mean, look at the equation. Do we have 10 grams of methane? Actually, no. It appears that we have 1 mole of methane. And that's the trick here, is that we have a mole of methane that is going to give us the negative 890.3 kilojoules. But if we only have 10 grams, how much heat would we get then? Okay, so basically what you're doing is you're taking a look at this question. You're saying, all right, well, the methane is going to be the limiting reagent. And when it runs out, your reaction stops. So how much heat would you create if you only had 10 grams? Now, what's going to be helpful is that this delta H value, this 890.3 kilojoules, notice in yellow I've added per mole reaction. Okay, that unit of measurement at the end there, per mole of reaction, is a very specific thing that we have to understand. What it means is that for this reaction, in these exact molar amounts, we will produce negative 890.3. So if we have exactly 1 mole of methane, 2 moles of oxygen, 1 mole of carbon dioxide, and 2 moles of water, we make negative 890.3. However, if you start changing any of those amounts, you do not necessarily make negative 890.3. You may make more, you may make less. But the point is that number, negative 890.3, is ridiculously specific to the molar amounts listed in the equation. Okay, the question that I've posed to you here about the 10 grams, I've obviously changed from the exact molar amounts in the problem, or in the equation, excuse me. So herein lies the mathematics that have to happen. And then again, this is how we can use this negative 890.3, because that value is specific to 1 mole, 2 moles, 1 mole, 2 moles, if I look at the molar ratios of the whole reaction. So let's take a look at how this works then. How much heat can be obtained from 10 grams of methane? Okay, so I hope that at this point you're kind of in your head thinking to yourself, all right, so I guess 1 in grams. convert to moles. So we'll start with that 10 grams, excuse me. And we will, of course, convert it to moles. Diagonal top to bottom, my grams will cancel, and I'm left with moles. And then this is where your delta H comes in, because notice that we started off in the problem 10 grams of methane, and we're asked not to go into another chemical, but just to give more information about this methane. So we don't have to use a molar ratio because we're not trying to convert between one molecule or another. Instead, now we're going to use our enthalpy. So take a look at what I'm going to do. I'm going to say I want to put that 1 mole of methane on the bottom. And by the way, the 1 mole here is because there's 1 mole here. So this 1 mole of methane is going to be able to produce for me the negative 890.3, and the moles cancel. The grams already canceled. That leaves me with kilojoules, and that tells me I've got negative 556 kilojoules of heat that I could actually produce at this point. So again, hopefully that makes sense. It's less, right? 10 grams of methane is not a mole. In fact, as we say here, 16 grams is a mole. So if I have less than a mole, I would produce less heat given off in my exothermic reaction. So again, you're seeing here how the negative 890.3, this enthalpy value, can actually be used as a conversion factor to give you specific information about whatever reaction you may be doing at the moment. So this is where you're going to want to pull out your printed out pages from the Ebbing textbook. If you flip to page 245, you'll find example 6.4 right in the middle of the page. And I say to look at the example and note that the conversion factor uses 2 moles of ammonia because 2 is in the coefficient of the equation. So again, just, and I'm looking at the pages right now, so look at those with me. They have a reaction here of nitrogen gas and then also hydrogen gas, and we're producing ammonia, and they give you a delta H value of negative 91.8. And then the question that they actually give you, how much heat is evolved when 907 kilograms of ammonia is produced according to the following equation. So again, this is a specific equation about 2 moles of ammonia, but they're specifying, well, we only used 907. Which is, in fact, is not only, it's actually a lot more than 2 moles. So if you go down where it says problem strategy and then under solution there, you'll see that they started off with the 907 kilograms, which they then converted to grams pretty much right off the bat. They used their molar ratio, or molar mass, excuse me, to get into moles. And then notice the conversion factor, the negative 91.8 over 2 moles of the ammonia. And again, that 2 that's in front of the 2 moles of ammonia, that comes from the equation that's listed above. They do the math, and then you have your final answer. So understand that when you're using enthalpy values as conversion factors, that your mole amount comes directly from a coefficient in the equation, okay? All right. So then on the same page, page 245, just looking at the exercise now, they're asking you how much heat evolves when 10 grams of hydrazine reacts according to the reaction in exercise 6.3. In fact, if you just look at the screen, I have that reaction for you, and I have the delta H value. So please do me a favor and try this yourself. Pause the video, and I'll show you the answer. Okay, the answer you should have come up with should be negative 164 kilojoules. Please note the use of the 2 here for the hydrazine, because this 2 came from this, and this 2 moles is specific to the negative 1049 that we used in our conversion factor. So hopefully you're okay on that. Ask me some questions when we get to class if you need, and we'll continue on. Okay, so we've now used the stoichiometry portion, and you're starting to see how these enthalpy values are kind of powerful. They actually give you another tool in your toolbox, like I mentioned. But we need to talk now about something called a thermochemical equation. What's kind of cool, you've actually been looking at these for quite a while. I'm just now going to tell you, hey, this is what they're called. I'm all about like hiding information from you, aren't I? No, not really. Okay, thermochemical equation. It's a long definition for something that really is pretty simple. Okay, read it with me. The chemical equation for a reaction with the phase labels that gives the molar interpretation, meaning that it's balanced, so it's got coefficients, and the enthalpy of reaction is also given. So this is a thermochemical equation. Notice that it is a balanced equation. Notice, and it just depends on the notation that they'll use. In this case, there's a semicolon here just to show a visual separation between the two parts, but there's the actual balanced chemical equation on the left, and then on the right side, they'll give you the delta H value or the enthalpy change for that reaction. That is a thermochemical equation. That's it. So we do want to understand that if we were going to describe to somebody what this equation was, that we can put it into regular words. Please just read those with me. 2 moles of sodium metal, again, you can see the phase labels, reacts with 2 moles of water to form 2 moles of aqueous sodium hydroxide and 1 mole of hydrogen gas, and it evolves 367.5 kilojoules of heat. So you'll want to keep in mind that for these thermochemical equations, you may be asked to write the thermochemical equation from the words, or suppose it could be vice versa, right? So note, the definition of thermochemical equation specifies phase labels, right? Did you miss that? Hopefully I made it a little bit clear going back with phase labels. With phase labels, so solid sodium, liquid water, aqueous sodium hydroxide, and gaseous hydrogen gas. This is incredibly important. Delta H is a state function. What that means is that the state of matter is of very high importance. In fact, if you take a look, you will actually find that delta H values are very much dependent on, in fact, the state of matter. In fact, do me a favor. In the same packet that we're working with today out of the Eqns textbook, just go all the way to the very back page. All the way to the very back page. And what you'll notice on that page is that it's table 6.2, standard enthalpies of formation. And let's see. We want to look for something that has 2 different states of matter. Actually, if you would just look under sodium, sodium's at the top left. Go down to where it says Na gas, and then right below that it says Na solid. And then look over at the 2 values. The sodium gas has an enthalpy of 107.8, and the sodium solid has an enthalpy of 0. So right there, it depends on the phase. That's why the phase labels are so important, because if you end up having the gaseous version versus a solid version, we have a very distinct difference in what those 2 chemicals bring to the table in terms of heat already. So it's a really big deal. And this really should make sense to you. When you think about a gas, its particles are more energetic, are they not? They're flying around all crazy, and they do have more energy, more internal energy, than the similar comparison to a liquid or a solid. Obviously, a solid is going to have the lowest enthalpy, and the liquid would have a little higher, and the gas a little higher than that. But just because you're a solid doesn't mean you have a zero. Doesn't mean that you have a 0 enthalpy. In fact, if you continue to look at the same table 6.2, go down to carbon, and notice that there's actually carbon gas, which has a pretty substantially endothermic, positive 715 enthalpy. Then there is carbon graphite, which is like, graphite from your pencils. That has an enthalpy of 0. And then diamond actually has a slight enthalpy. So please note that, you may be a solid, but you could still have enthalpy. In fact, what was the other one I was just looking at? Look under sodium. Look under the last 3 under sodium. There's NaCl, there's NaHCO3, and there's Na2CO3. And each one of those has a really substantially high enthalpy. So just because you're a solid doesn't mean that you have a 0 enthalpy. I guess I just wanted to make that clear. Hopefully that wasn't just a bunch of rambles. So in the case of these 2 equations, I just want to point out here that they look kind of very similar on the surface, do they not? They both have hydrogen gas, and they both have oxygen gas in the same molar ratio, and we have H2O with the same molar ratio, but here's a difference. We have the gaseous version versus the liquid version, and you can see 2 different enthalpies of reaction at the end of those 2 different equations. So in this case, again, more heat is released when the product condenses into a less energetic form of matter. So this is something that if you look carefully at the numbers, they really should make sense. again, more heat released here in the second equation when the product condenses all the way down to a less energetic form. Obviously, a gas is highly energetic, whereas when you bring it all the way to a liquid, you release a little bit more of that energy, and then the values certainly match it up. So that's good. All right, so flipping to page 242, going back a couple pages, seems sort of weird to go back. Back to page 242, example 6.2, I ask that you just sort of take a look at it. So please do me a favor and just read it. Read the problem itself and also read the solution and make sure that you understand it, and then just pause the video while you do that. Okay, so now that hopefully this actually makes sense, really what they're doing is they've just given you words and they're asking you to write the thermochemical equation. Now I ask that you try exercise 6.3. Pause the video. Okay, and your answer for this would be 2 N2H4 liquid plus N2O4 liquid yields 3 moles of nitrogen gas and 4 moles of gaseous water. You could say water vapor, obviously. And then your little semicolon, and then your delta H equals negative 1049 kilojoules. Cool. All right. So the last little point that we'll make with this presentation today is how we can manipulate these thermochemical equations. So in the previous example, you were given some information, you were told a few different things, and you had to just kind of put it all together. And now we're going to be asked to do a little bit of work with them. So it may seem like what I'm about to do on this slide is sort of like, wait, what am I going to use this for? But please just kind of hold that thought, and I will show you 2 examples after this slide. Okay, so we have some rules to live by when we have to manipulate thermochemical equations. When a thermochemical equation is multiplied by a factor, the value of delta H must also be multiplied by the same factor. In other words, it kind of reminds me of algebra. If you're trying to solve for x, and in order to get x by itself, you've got to divide by 2, then I need to divide everything by 2. And it's the same thing. So specifically, this states multiplying, but multiplying and dividing are very, very similar. So when you do something to the equation, you're also going to do the same thing to the delta H, multiplying or dividing. And then the second thing is there will be times in which we're actually going to, in our manipulation of these equations, we'll reverse the equation. We'll make the products the reactants and the reactants the products. And we're going to then do a similar mathematical thing by reversing the sign of delta H. So if delta H was negative and we reverse the equation, it is now positive. Okay, now this is going to really come into play starting with our next, gosh, it's like a simple word. What am I looking for? Presentation. My goodness. Yeah, so this is going to really come into play with our next presentation, but I want to introduce it now because it starts to have you understand that you won't just be writing them from words, but you'll actually be working with them a little bit. So let me give you 2 examples that show you what I mean by these 2 rules. Okay, example for rule 1. Here we are faced again with this equation for creation of ammonia. The enthalpy is a negative 91.8 kilojoules. That's an exothermic reaction. And let's just say we wanted to add another mole of nitrogen gas to the whole mixture. Okay, well, if we add another mole, really what that would make us do in order to write a proper thermochemical equation is we would actually have to multiply everything by 2 because otherwise it won't be balanced. So if we have another mole of nitrogen, then we've got 6 of hydrogen and 4 of ammonia. So what would then be the enthalpy of that reaction? Well, if you said something like, well, I don't know, maybe we should multiply it by 2 because that's what we did with the whole reaction, then you would be dead on. So multiplying the negative 91.8 by 2, we get negative 184 kilojoules. So you can see again that this is dependent on the amount of chemicals that we have. It's an extrinsic property. It depends on how much you have. So if I have less, I can make less heat. If I've got more, I can make more heat. Okay? Okay, it's an extensive property. Forgot that was up here. Depends on the amount of the sample. Okay, did you get that? Extensive. All right, so example for rule 2, we're going to deal with the same exact equation, but let's say we want to run it backwards. Let's say we made a whole bunch of ammonia, but oh man, we need nitrogen gas and hydrogen gas now. I don't know why we would do that, but maybe we do. Okay, so we have to reverse the equation. So here we have now just simply flip-flopped our reactants and products, and what will be the effect of our delta H? If you said, well, you should probably reverse the delta H, then you would be correct. I should have like an applause machine here with me. So if you reverse the reaction, we go from a negative 91.8 to a positive 91.8. That should make so much sense. Reactions are either endothermic or exothermic. And so the way that it's written, if it's exothermic, if you flip it and do it reverse, it's going to make it go the other way. It's going to be endothermic. So it really makes a lot of sense. And like I said, as we continue on, we're going to be seeing how we're really going to be using this. So you're getting some introductory information. You're understanding how to use stoichiometry with this delta H value. You're understanding what a thermochemical equation is, how to manipulate them in the basic forms. And then with our next presentation, we're going to take it to the next level. So that is it for today. Record your questions and we'll talk tomorrow. See you later. Bye.